In this video, we will talk about injective and surjective functions. Such functions are also known as one-to-one and onto. These are essential ideas that come up again and again in higher mathematics, and there's often a lot of confusion by students over what these terms mean and how to prove that a function does or does not have this property. Before we discuss injectivity and surjectivity, we need to talk about what a function is. We've seen many examples of functions in our various math courses, and almost always they come with some sort of formula attached to them. That may be a good way to introduce functions, but it may not be the best way to think about functions in the long run. A more abstract way of thinking about a function is in terms of what you might call a function machine. The machine will do something with your input and generate an output. Maybe there's a formula inside the machine, maybe there's a lookup table, maybe there's an algorithm, or maybe there's no describable pattern at all. The function may operate as a black box. The key is that each input generates exactly one output. A function cannot spit out two or more elements, and it can't spit out 0 elements for a given input. The set of things that you're allowed to plug into your function, the set X in this picture, is called the domain. The set Y that catches all the outputs is called the codomain. The set of things that actually come out of your function is the range. The range is a subset of the codomain, but it may not be the entire codomain. Let's look at a simple example of a function. Here we have a set X, the domain, that consists of 4 animals, and a set Y, the codomain, that consists of 5 types of food. The arrow diagram illustrates a function because each element of the domain corresponds to exactly one element of the codomain. In this case, the giraffe maps to the pretzel, the dog maps to the taco, the monkey maps to the apple, and the owl maps to the Swiss cheese. So this is a perfectly good function. If we modify the arrow diagram to get this slightly different relation, we obtain something that does not represent a function. In this case, we see that the monkey does not map to anything in the codomain, so that's a problem. Another problem is that the owl maps to 2 things, the apple and the cheese, and that is also forbidden for a function. If you're in a situation where your domain and codomain are the real numbers, or some subset of the real numbers, then you might want to take advantage of what we call the vertical line test. The vertical line test says that a curve in the plane is the graph of a function if and only if every vertical line crosses the curve exactly once. Here's an example of a curve in the plane, and we're imagining that the proposed domain of this function is the set A. As you can see, if we draw any vertical line from the domain upward, it will cross the curve exactly one time. So this is the graph of a function. On the other hand, consider this curve in the plane. If we draw this vertical line, it crosses the curve twice, and that's not allowed. Moreover, this second vertical line does not cross the curve at all, and that's also forbidden. So this is not the graph of a function. Okay, now that we're familiar with functions, we're ready to talk about injective functions, also known as one-to-one functions. The definition looks complicated. It says that the function f from x to y is injective, or one-to-one, provided that for all x1 and x2 in the domain x, if f of x1 equals f of x2, then x1 equals x2. This is a nice mathematical definition and one that you will need to know in order to prove that functions are injective, but it's probably more intuitive to think about this property using an equivalent form of the definition. You may know from the study of logic that an if-then statement is equivalent to its contrapositive. We get the contrapositive of an if-then statement by interchanging the hypothesis and the conclusion and negating them both. The statement if A then B is logically equivalent to if not B then not A. In the case of our definition of injectivity, we get the equivalent contrapositive if x1 is not equal to x2, then f of x1 is not equal to f of x2. That is, if we plug in any 2 different elements of the domain, we get 2 different elements of the codomain. Here's an example of an injective function from the set x to the set y. We can see that this function is injective because if we take any 2 elements of the domain, let's say the giraffe and the monkey, then they map to two different elements in the codomain, the apple and the pretzel in this case. And you can say the same for any pair of elements in the domain. On the other hand, if we change our function a little, like this, we now have a function that is not injective. Two different elements in the domain, the giraffe and the monkey, both map to the pretzel, so it's not one-to-one. Just like we had a vertical line test to determine whether a curve is the graph of a function from the real numbers to the real numbers, we also have a horizontal line test to test whether the graph of a function is the graph of an injective function. The horizontal line test says that a function is injective if and only if every horizontal line crosses the graph of the function at most one time. Here's an example of the graph of a function on the domain A. Here's a horizontal line that crosses the graph one time. Here's a horizontal line that crosses it 0 times. And you can see that any other horizontal line will either cross 0 or 1 time. And so this is the graph of an injective function. On the other hand, the second graph is a perfectly good function, but we can see that this horizontal line crosses the graph twice, and therefore it does not represent an injective function. Notice that there are places where horizontal lines cross 1 or 0 times. That's fine, but because there is the horizontal line that crosses it twice, we know that it's not injective. Okay, so you might be given a function, and you might be asked to prove that the function is injective. Let's talk about how that would go. Following the definition, we need to begin with two arbitrary elements of the domain and assume that they give you the same value when you plug them into the function. So that's the first line of your proof. Then the middle part of your proof requires showing in some rigorous way, perhaps using algebra or some other technique, that in fact x1 equals x2. That is, you're showing that the only way that f of x1 could equal f of x2 is if x1 and x2 are actually the same element of the domain. If we're able to do that, then we conclude that our function is injective. And this gives us our general template for a proof of injectivity. Let's look at a concrete example. Consider the function f in which the domain is the interval from 2 to infinity and the codomain is the set of real numbers. The function is given by the formula 1 over 2x minus 4, and here is a graph of the function. Notice that every horizontal line crosses the graph 1 or 0 times, and so the horizontal line test tells us that f is 1-to-1. But that's not a proof. Let's give a rigorous proof that f is injective. We start with the assumption that we have 2 points, x1 and x2, in the domain that yield the same output from the function. In other words, when we plug them in, we have that 1 over 2x1 minus 4 equals 1 over 2x2 minus 4. Because these values are equal, we can take reciprocals of both sides. That gives us 2x1 minus 4 equals 2x2 minus 4. We can add 4 to both sides. That tells us that 2x1 equals 2x2. We divide both sides by 2 and conclude that x1 equals x2. And that's where we needed to end up, and therefore our function is injective. Now let's discuss how to prove that a function is not injective. This is, relatively speaking, easier to do than proving a function is injective. We must simply give an example. That is, we must produce two different elements of the domain that yield the same output. In this case, our function is the function f of x equals x squared, viewed as a function from the real numbers to the real numbers. And there are many examples we can choose from. Any positive number and its negation will work. For instance, 2 and negative 2 are two different elements of the domain, but both f of 2 and f of negative 2 equal 4. Thus, f is not injective. The idea of injectivity can be a source of confusion for students. Why is that? I think the name itself can be the source of confusion. Not injectivity, but one-to-one. Some people read one-to-one with a mental emphasis on the second one, one-to-one. That is, they're reading it as if the negation of one-to-one is one-to-multiple. In other words, they're interpreting one-to-one to be one element of x maps to only one element of y. But this is not what it means to be an injective function. This is simply what it means to be a function. Each element in the domain maps to exactly one element of the codomain. Better is to put the emphasis on the first one to one. The negation of 1 to 1 is multiple to 1. We want to avoid multiple elements of the domain mapping to the same element of the codomain. But even this interpretation isn't perfect, because for an injective function, we could have 0 elements of the domain mapping to a given element of the codomain. So if we want to accurately unpack the name 1 to 1, we might say, at most one element of x maps to one element of y. And that's a mouthful. We could propose a better name than 1 to 1, such as 0 or 1 to 1. That does a pretty good job of representing the meaning, but it doesn't exactly roll off the tongue. Another possibility could be 2 to 2, which indicates that 2 different elements of the domain must map to 2 different elements of the codomain. Sadly, we're probably not going to be able to dethrone 1 to 1. Perhaps we should just stick with injective. Another problem is that the definition of 1 to 1 is confusing. As we discussed earlier, the contrapositive of the definition is more intuitive than the definition itself. It says that if you have 2 different elements of the domain, then they will produce 2 different elements in the codomain. But the definition is what we must use in the proofs of injectivity. A tricky aspect for some students, I think, is that we're introducing 2 elements of the domain with 2 different names, x1 and x2. But then we want to prove that they are, despite having different names, actually the same. And that's confusing. Now that we understand injective functions, let's look at surjective or onto functions. The definition states that a function f is surjective or onto, provided that for every y in the codomain, there exists an x in the domain such that f of x equals y. That is, everything in the codomain is hit by some element in the domain. Another way of thinking about onto is that the range of the function is equal to the codomain of the function. This might seem like an intuitive definition, but often it's confusing to work with. It's confusing because usually when we work with a function, we start off with an element of the domain and we produce an element in the codomain. But to prove that something is onto or surjective, we have to think in the opposite direction. We begin with an element y in the codomain, and we have to determine that there exists an element in the domain x that maps to y. Here's an example of a surjective function g from the set A to the set B. Indeed, if we march through the elements of the codomain, each element has a corresponding element in the domain that maps to it. Consider the giraffe. The taco maps to the giraffe. If we look at the dog, the apple maps to the dog. If we look at the monkey, there happens to be 2 elements, the pretzel and the cheese, both of which map to the monkey. And if we look at the owl, the birthday cake maps to the owl. So this function is surjective. If we were to change the function slightly, such as this, then it's no longer surjective. In this case, there is no element of the domain that maps to the dog. So this new function is not surjective. Again, we often want to know about surjectivity for functions from the real numbers to the real numbers. Just like there was a horizontal line test for injective functions, there's also a horizontal line test for surjective functions. In this case, a function is surjective if and only if every horizontal line crosses the graph at least once. Consider this first example. In this case, we see that any horizontal line we draw crosses our graph 1, 2, or 3 times. So this graph is the graph of a surjective function. On the other hand, the second example is not the graph of a surjective function, since we can find a horizontal line that never crosses the graph. Sometimes you'll be asked to prove that a function is surjective. This proof is often trickier for students than proofs of injectivity, and again, the reason is that we start with an element of the codomain, and we need to produce an element of the domain. So we begin the proof with a generic element little y in the codomain capital Y. In the middle of the proof, we're going to have to find some element x in the domain that maps to our arbitrarily chosen little y. In order to find this element little x, you will likely have to do some work ahead of time on scratch paper. Once you do that work ahead of time, you present the x value in your proof and show that it produces y when it's inserted into the function, and that will complete our proof. Okay, let's see how this would work with an actual function. Our objective is to prove that the function f of xy equals x squared plus y cubed plus 2 is surjective. Before we start, it's important to recognize that this is a function of two variables. That means that the domain is r squared, and a typical input is an ordered pair x comma y. The output of the function is a single real number, and so the domain is r. As we've discussed earlier, we often have to do some work ahead of time on scratch paper. Let's do that now. Let's pick an element in the codomain. In this case, that's a single real number. We'll call it z. We must find an ordered pair, x comma y, in the domain that maps to z. As it turns out, there are infinitely many such elements. This function is not one-to-one, it's infinitely many-to-one. Although there are many inputs that will map to z, we need to find an expression for a single element of the domain, x comma y, that maps to this generic z. That is, we want to find an x and a y such that this equality holds. If you start playing around with this expression, you'll realize that if we set x equal to 0, then all we must do is find a y where y cubed plus 2 equals z. We can do some basic algebra and conclude that the cube root of z minus 2 will do the trick. So this scratch work tells us what our x and y can be, and we'll get our ordered pair 0, comma, the cube root of z minus 2. Remember, this is one of many possible solutions. We set x equal to 0, but we could have set it to be some other value and then solve for y. Finally, notice that this ordered pair is expressed in terms of our generic element z. That is going to be essential. Now that we've done our scratch work, let's look at the proof. We're going to start with our generic z in the set of real numbers, which is the codomain. Then we'll introduce the ordered pair that we found earlier, 0, comma, the cube root of z minus 2, which is an element of the domain, r squared. This short sentence is hiding all of the work that we did earlier. When we plug that element into the function, we get 0 squared plus the cube root of z minus 2, quantity cubed, plus 2. When we cube the cube root, we get z minus 2. Then the 2 and the negative 2 cancel, leaving just z. And therefore, we conclude that our function f is surjective. So again, we started with a generic element of the codomain z. We found an element of the domain that maps to z, and this is our procedure for showing that the function is surjective. Now let's show that a function is not surjective. As with injectivity, we must only give an example. In this case, we must produce an element of the codomain that is not in the range of the function. Again, let's look at our function f of x equals x squared as a function from the real numbers to the real numbers. We know that we will never get a negative value out of this function. To show that this function is not surjective, we only need to give one such value. In particular, negative 2 is an element of the codomain, but there is no real number x whose square is negative 2, so f is not surjective. A student's confusion with the idea of surjectivity can come in a number of places. The most basic problem is to confuse onto with into. Every function maps into the codomain. That is, given any x in the domain, f of x is in the codomain. But some students think that this is what onto means. Instead, onto means that the domain fully covers the codomain under the action of f. That is, every y in the codomain is in the range of the function. In my experience, a more common problem is for students to have difficulty proving that a function is surjective. Many students have trouble right at the beginning of the proof. As we've already discussed, these proofs must start with a generic element of the codomain and not, as you might expect, with an element of the domain. Next, after starting with an element of the codomain, the objective is to find an element of the domain that maps to the given element. This process is not obvious and may be a source of the problem. Even finding the right language to describe what you're doing may be difficult. We want to go backward from the codomain to the domain, but unless the function happens to be both surjective and injective, the function f does not give us a function that maps backwards from the codomain to the domain. So we do not want our language to imply this. Now that we understand injective and surjective functions, we're ready to discuss bijective functions. A function is bijective if it is both injective and surjective. As an example, suppose C is the set of musical instruments and D is the set of animals. The function h from C to D is a bijective function because it is both one-to-one and onto. Notice that in this case, both C and D have 4 elements in them. In general, in order for there to be a bijective function between two finite sets, they must have the same number of elements. One nice property of bijective functions is that they're invertible. So we could turn all of these arrows around and get a function h inverse from D to C. This is the arrow diagram for h inverse. Under the function h, the piano mapped to the dog. Now, with the inverse function, the dog maps to the piano. Previously, we had the saxophone mapping to the giraffe, and now we have the giraffe mapping to the saxophone, and so on. Proving that a function is bijective has 2 parts. That is, it requires 2 separate proofs. First, we must prove that the function is injective, and then we must prove that it is surjective. Let's end with one more example. The function f of xy equals x plus y, comma, negative x. The domain and the codomain of f are both r squared. That is, this function takes an ordered pair of real numbers as an input and spits out an ordered pair of real numbers. We would like to prove that f is bijective. First, let's prove that it's injective. Recall how such a proof begins. We start with 2 elements of the domain, 2 ordered pairs in this case, and assume that they produce the same output from the function. That is, the ordered pair x1 plus y1, comma, negative x1 equals the ordered pair x2 plus y2, comma, negative x2. In order for these 2 ordered pairs to be equal, the first coordinates must be equal to each other, and likewise, the second coordinates must be equal. So x1 plus y1 equals x2 plus y2, and negative x1 equals negative x2. From the second of these equalities, we see that x1 equals x2. When we substitute this into the first equality, we obtain x1 plus y1 equals x1 plus y2, and hence y1 equals y2. Because x1 equals x2 and y1 equals y2, the ordered pair x1 comma y1 equals the ordered pair x2 comma y2. So we have shown that f is injective. Now let's prove that f is surjective. Again, we'll have to do some scratch work ahead of time. We begin with a generic target element, z comma w in the codomain. We want to find an element x comma y in the domain such that f of xy equals z comma w. When we plug xy into f, we get x plus y comma negative x. So we need x plus y comma negative x to equal z comma w. If they are to be equal, the first coordinates must be equal, as must the second coordinates. That is, x plus y equals z, and negative x equals w. At this point, we need to solve these 2 equations for x and for y in terms of z and w. From the second equality, we conclude that x is equal to negative w. Substituting negative w in for x in the first equation, we obtain negative w plus y equals z, so y equals z plus w. Thus, our desired input is negative w comma, z plus w. And now we're ready to give the proof. We begin with a generic element of the codomain, z comma w, and now we use our scratch work. We identify the element negative w comma z plus w in the domain. When we plug it into f, we get f of negative w comma z plus w equals negative w plus z plus w comma negative w. And this all simplifies to z comma w as we needed it to and as we knew it would, and therefore we conclude that f is surjective. Finally, step 3, because f is injective and surjective, we conclude that it's bijective. Moreover, because f is bijective, it's invertible. That is, there exists an inverse function going from the codomain of f to the domain of f. Our scratch paperwork for the surjectivity proof was essentially the process of computing the inverse of the function. And so we're not going to show the work here, but we conclude that f inverse of z comma w is negative w comma z plus w.